Myself Shivkrishnan V. Nair, student code PCM 25314, presenting on behalf of Team 7 for the course CM 4003, Construction Project Execution Monitoring and Control under the Faculty of Technology. Our project is based on an in-situ slum redevelopment project located in Ahmedabad. This presentation includes the project brief, pre-construction activities, QA/QC laboratory planning, and value stream mapping carried out to study project execution, monitoring systems, quality control processes, and lean construction improvements within the redevelopment project. I will be presenting our study on construction project execution, monitoring, and control for an in-situ slum redevelopment project located in Ahmedabad. The project is being developed under the PMAY Urban Slum Rehabilitation Policy 2013 using a PPP turnkey model with a design, build, finance, operate, maintain, and transfer approach. The total project cost is approximately 150 crores with the work starting in June 2023 and proposed completion in March 2027. The project is a brownfield redevelopment plan in 4 phases over a site area of around 31,678 square meters. The development consists of 19 residential towers of G+7 floors, providing 2,170 rehabilitation housing units along with 36 shops. The primary objectives of the project are to provide safe and dignified housing, improve urban infrastructure, and optimize land use while ensuring affordable rehabilitation housing for all the residents. Moving to pre-construction activities. So the site establishment and layout planning. Moving to the pre-construction phase, detailed site establishment planning was carried out to ensure smooth project execution. The site layout was organized using peripheral zoning where temporary facilities were placed along the edges to maintain clear construction zones at the center. Dedicated areas were provided for reinforcement yards, formwork yards, QA/QC labs, offices, storage spaces, canteen, waste storage, and equipment resting areas. Separate entry and exit points with security cabins improved access control and traffic movement within the site. Centralized placement of offices and QA/QC facilities improved supervision and coordination between contractors, PMC teams, and engineers. The labor colony was also carefully planned considering workforce welfare. The project had a peak labor strength of around 1,500 workers with approximately 720 workers requiring accommodation. Facilities such as dormitories, family accommodation, toilets, bathing areas, kitchen, dining spaces, laundry, recreation zones, and crash facilities were provided. Overall, the plant layout improved internal circulation, material handling efficiency, worker welfare, and overall site management. This slide presents the electrical planning and distribution system developed for the site. The connected electrical load was calculated by considering construction machinery, water systems, administrative facilities, labor colony requirements, steel yards, and lighting loads. The total connected load came to approximately 93 kilowatts. After applying a diversity factor and spare capacity, the final requirement was estimated at around 133 kilowatts. The electrical distribution network consists of a main distribution board, multiple sub-distribution boards, local tower meter boards, earthing pits, and distribution lines across the site. The estimated capital cost for the electrical setup was approximately 2.55 lakhs, while the expected monthly electrical expense was around 74,000. This planned distribution system ensured uninterrupted power supply, safe electrical operation, and effective load management through the construction period. Moving to plumbing and water supply planning, water storage requirements were estimated for various activities including batching plant operations, construction activities, labor colony usage, and canteen facilities. The minimum storage requirement was calculated as 105 kiloliters after considering a suitable factor of safety. The proposed plumbing network included HDPE and UPVC pipelines, borewell pumps, pressure pumps, valves, and distributed storage tanks across the site. 10 syntexed water tanks of 10,000 liter capacity were proposed for storage and distribution. The total plumbing infrastructure cost was estimated at approximately 15.6 lakhs. The plant water supply system ensured continuous water availability for construction operations as well as domestic usage within the labor colony. QA/QC laboratory. QA/QC documentation system. Quality control on the project was primarily documentation driven to ensure traceability and compliance with specifications. Several registers were maintained on site, including cement receiving registers, steel test registers, RMC registers, cube casting registers, cube test result registers, slump test registers, and material sampling registers. Supporting documentations included tender specifications, GFC drawings, structural and architectural drawings, bar bending schedules, mixed design approvals, manufacturer test results, and also laboratory reports. The QA/QC process followed standards such as CPWD Works Manual to 2024, CPWD Quality Assurance Manual, IS codes, AMC specifications, and NABL testing guidelines. Material approved followed a systematic workflow starting from material receipt, register entry, sampling, laboratory testing, recording of results, verification by PMC or the client, and finally approved for usage in works. Existing QA/QC laboratory analysis. This slide presents the analysis of the existing QA/QC laboratory setup. The laboratory supported essential on-site tests such as slump testing, compression testing, tube curing, sieve analysis, and material inspection. However, several limitations were identified in terms of workspace efficiency and equipment availability. The existing laboratory area was only around 10 square meters, which resulted in congested movement and limited testing efficiency. Several important equipment such as sieve shakers, hot air ovens, moisture meters, bycat apparatus, and Le Chatelier apparatus were not available on site. The analysis highlighted the need for improved zoning, dedicated curing areas, better storage, and enhanced equipment provision to improve testing operations and workflow efficiency. Proposed QA/QC laboratory layout. To address the identified issues, a proposed QA/QC laboratory layout was developed. The updated laboratory increased the total area from 10 square meters to 36 square meters, including a dedicated 15 square meter curing tank area included. The proposed layout introduced a clear zoning for measuring equipment, cube stacking, curing tanks, testing areas, and resting spaces. Additional equipment such as sieve shakers, moisture meters, bycat apparatus, and Le Chatelier apparatus were incorporated to improve testing capabilities. A submersible water heater was also proposed to maintain the proper curing temperature conditions. Overall, the redesigned laboratory improved testing workflow, safety equipment accessibility, documentation control, and quality monitoring efficiency. Value stream mapping, current state mapping, and defects observed. This slide presents the value stream mapping study conducted for AAC blockwork activities at 5th floor of I block. The observed activity involved AAC block installation using a crew of 3 masons, 1 helper, and 1 block cutting machine operator. The total observed work duration was 465 minutes, including lunch break. The current state mapping identified major non-value added activities, particularly weighting and over-processing. Weighting occurred mainly due to lack of pre-mixed mortar and pre-cut blocks before execution. Over-processing occurred because of repeated alignment checks during each layer of blockwork. A defect was also observed due to incorrect mortar thickness in one wall layer, which resulted in a rework. The analysis showed that out of the total 410 minutes of cycle time, only 186.5 minutes were value added, while 223.5 minutes were non-value added activities. This resulted in an overall process efficiency of only 45%. Lean tools and future state mapping. To improve the workflows, several lean construction tools were proposed and implemented. The lean tools included 5S, standard work procedures, just-in-time material delivery, visual management, Kaizen, Kanban systems, Pokayoke error proofing, and improved work cell layouts. Tag time analysis showed that the planned tag time was approximately 12.96 minutes per square meter, whereas the observed tag time was 14.59 minutes per square meters, indicating lower productivity than planned. After the implementation of lean tools, The future state mapping reduced total cycle time from 410 minutes to 308 minutes, which is nearly a 25% reduction. The tag time improved from 14.59 to 9.5 minutes per square meter without adding additional resources. The study demonstrated that proper material preparation, workflow standardization, and organized site coordination can significantly improve productivity and reduce waste in construction operations. To conclude, this study demonstrated the importance of integrated planning, monitoring, and quality control in improved construction project execution. The pre-construction planning established an organized framework for site operations through efficient zoning, utility planning, workforce management, and safe circulation systems. The QA/QC system strengthened quality assurance through structured documentation, material traceability, systematic testing procedures, and improved laboratory infrastructure. The value stream mapping study successfully identified major inefficiencies such as waiting, overprocessing, and workflow interruptions in AEC blockwork activities. Implementation of lean construction tools significantly reduced cycle time, improved takt time, and enhanced productivity without requiring additional manpower or resources. Overall, the study highlights how proper execution planning, quality monitoring, and lean construction practices can improve efficiency, coordination, safety, overall project performance in large scale development projects. Thank you.